So the topic of today is going to be about probabilistic inference. Last time we gave some basic rules of probability and kind of talked about probability as a whole. It was meant to be, as I said, kind of a review, but some new stuff as well. But today I mainly want to focus on the topic of graphical models and probabilistic inference in these graphical models. In particular, I want to focus a little differently than I did in the past, so we'll see how it goes. But I think the way that graphical models are usually taught is there's a lot of time spent on exact inference methods, which, while sort of theoretically nice and kind of having nice graph algorithms for them, they really aren't used very much in practice, just because almost all graphical models really care about, you actually cannot run exact inference techniques for them. So instead, I'm going to be mainly focusing on sample-based inference methods today. And in particular, I'll actually go through a pretty detailed proof of the Metropolis-Hastings algorithm, which is one of kind of the workhorses of sample-based probabilistic modeling. And we'll sort of go through that algorithm and talk about why it works. And then really next time, we'll see the application of that to these graphical models. And in particular, we'll see it in terms of Bayesian modeling. We'll see how techniques like Bayesian modeling really use these kind of sample-based methods to sort of replace a lot of the maximum likelihood-based estimates that we've talked about so far in class. A few points before we start, though. The first thing is that and I'll actually show one more thing before I get started on this as well. The first thing is that the class project proposals are due this Wednesday, I believe, right? Wednesday at 12. All deadlines are 12 p.m. unless otherwise mentioned. One comment we've gotten a lot of sort of questions about is, to what extent do these have to be kind of novel research versus can you just sort of implement something that already exists, or can you kind of try something, your own idea on some problem? And I sort of have two rules of thumb for this, though Ariel can also chime in about his opinions on this. So you're welcome. It doesn't have to. The project used in class does not have to be on the same level of, say, publishable computer science AI research, right? We're not assuming that of everyone here that you will publish your paper. It could be, actually. There's plenty of people that will be doing publishable work here, but it does not have to be at that level. At the same time, you should not be ignoring all existing work on some topic and just sort of making up your own approach to some problem that with kind of ignoring any literature search or kind of the vast body of work that already exists. So what I'd recommend is, if you are interested in a topic, do some pretty thorough searches, and Google's a great resource here, about other, literally type, AI plus whatever topic you're working on, or machine learning plus whatever topic you're working on. The chances are there is some published academic work in this area. If not, then you can talk with us too. That's great. You found a new area, but there's a good chance there probably is. And if so, read that work and try to situate yourself in respect to that work. That could mean you're implementing some existing algorithm on a new problem or a slightly different problem, or maybe you're just evaluating several different algorithms from the literature on a problem of domain that you have of interest. These kind of projects end up being much better than if you just kind of make up your own technique for solving some problem and don't relate it to what else sort of exists in the literature. So it does not have to be kind of novel research-wise, but it does have to kind of situate itself within the context of what else is going on academically and research-wise. Do you have any other comments on that?
I can maybe just expand on that. We had a couple of questions about this one example of, like, I'm interested in algorithm X. I want to implement algorithm X and test it in some data sets. So this is fine, but we do want at least the empirical evaluation part to be novel, in the sense that we don't want to just repeat the experiment done in an existing paper, but we add some novel element of, here's a new domain that I want to test this algorithm in, or just a new data set that people haven't looked at before. So that, but on a high level, it feels fine to focus on existing algorithm.
Yeah. Okay, so are there any questions about that? Also, the proposal phase is meant to be a feedback phase, right? So you're actually meant to we're going to respond to the proposals, and it's meant to be a feedback round, and you can change, ideally not completely, because then you miss one round of feedback, but you can certainly adjust your topic based upon the feedback we get you. So we're trying to get to everyone that sort of asks us to meet about these things. We might not get to everyone. I'll try. If we can reply over email, that's far preferable. So if you can send your questions over Piazza or over email, it's far preferable. But for the few outstanding people that have emailed us, or me, we'll try to get back to you and find a time, but I'm not sure we'll be able to do it before Wednesday. We'll try though. Okay, so the one other thing I would like to actually talk about here before jumping into probabilistic graphical models actually was the last slide from last time, or one of the last slides from last time. So last time I talked about maximum likelihood estimation and probabilistic kind of modeling. And I actually just wanted to show a very quick, I won't write anything down here, but I just wanted to highlight in the slides a very quick derivation of where that loss function that you're working on in the homework actually comes from. So we sort of told you this thing, right? We sort of told you that the loss function is this log of the sum of the exponentials of this thing minus a linear term here. And that looks kind of odd. I mean, why did we actually pick that as our loss function? So actually what's happening here is that just like before in the logistic regression case, which I covered last time, we're assuming that the probability of that y is equal to a given class j is proportional to the exponential of some theta, the inner product of some theta and the feature vector for that input, right? So we assume that p of y equals j given x is proportional to the exponential of the inner product of theta j and x. And of course that's nice because that's a positive number. So if it were negative, that would be hard to make a probability of that. It's a positive number, but we have to normalize it by, of course, the sum over all possible j's, right? So the actual probability that y equals j given x is equal to that same term, but now normalized over the sum over all other possible classes, or actually all classes including that class. And so that term there is the probability. Now if you assume that's the probability and you sort of just follow the rules of maximum likelihood estimation, you wind up at the exact loss function that you see in your homework, which goes with the name of softmax loss or cross entropy loss or other things like this. So that's where that comes from. It seems a little bit odd. I mean, you can kind of justify it just by looking at the terms there individually, but really that's the origin of that loss function. Okay, so as I said, I want to spend the majority of the time today talking about probabilistic graphical models and probabilistic inference. So are there any questions before I start? All right, so let's jump into probabilistic graphical models. Graphical models are sort of, as I said, kind of one of the workhorses of AI, actually. And they stem from the fact that while probability is great, sort of the models we talked about so far are great, they run into a bit of a headache once you start talking about trying to model distributions over large objects, right? Over variables that can take on many different values. So think about representing some distribution p of x, right? Where x represents here a large set of random variables. And in fact, suppose even that x here is just going to take on values between binary values. There's going to be n of these, right? So very naturally now, the number of assignments that we have to specify in order to specify that distribution is going to be 2 to the n, right? Because there are 2 to the n possible settings. And although we do solve some problems that have 2 to the n possible values. Actually, can we see is this visible? No, in the past we need to turn the lights there. Is the board visible?
It is, but if you turn the light on.
All right, let me try. Better? Okay. If we have to represent the probability over all possible assignments to these variables, this is going to be a very just not a practical approach for these problems, right? And so really what probabilistic graphical models are they are a way to represent distributions over large objects when there are certain independence properties that sort of are present in that distribution. Okay? And also note, I'm going to use the terms probabilistic graphical model and Bayesian network kind of interchangeably. We're really going to talk about generative models, these kind of things too, but I'm not going to sort of differentiate too much in this lecture between them. Though know that there are other graphical models that are not Bayesian networks, but I'll mainly be focusing on Bayesian networks here. So the simplest model that we're going to deal with here is in fact called a Bayesian network. It's going to be the primary subject of our discussion for this lecture. And formally, it's represented by two things. So I'll try to give a lot, I mean, this is the formal definition. I'll try to give a lot more intuition about what is actually saying about these random variables. But I want to give the formal definition first, and I'll try to elucidate some of the details. So a Bayesian network is specified by two things. A graph G, which contains a set of vertices and edges. I'll just call it like this. And V here is going to include all the variables that we have in our distribution. So V is going to, the vertices of our network equal, in fact, x1 to xn. And there are some edges too. And this is going to be a directed graph we're talking about here. Okay, so it's a directed graph, and in fact, it even has another property, which is that it is an acyclic graph. So there are no cycles in this graph. So this is this thing called a DAG, a directed acyclic graph, over the variables corresponding to random variables, and the vertices corresponding to random variables, and some edges. And there's also a set of conditional distributions. So this is the first thing it has. The second thing it has is a set of conditional distributions of each variable xi given the parents of xi. So wherever the parents of xi in the graph are, we need to specify a distribution of what values xi takes on, or the probability it takes on certain values, given the setting of all its parents. So we'll talk about an example of this in a second, but this is sort of the generic definition. And really, while I think it's important to sort of know the generic definition, I'm going to transition pretty quickly into a slightly different form called a generative model, which I think gives a little bit more of an intuitive understanding about what these things are really, or about sort of what these things look like in practice. And actually, this set now, these two things, define the joint distribution over all x as just equal to the product from I equals 1 to n of probability of xi given the parents of xi. And typically we're going to assume actually that the variables are ordered in what's called topological ordering, so that all the parents of a variable j always come before j in the ordering, but which exists for any directed acyclic graph. But we're not going to worry too much about that here. I mean, we're not going to get into those kind of details here. Now, equivalently, actually, another definition of this, which is not that obvious, but it's not also that hard to show, is that xi is independent of non-descendants, meaning variables that are not descendants of itself, given of all variables that are not descendants of that variable, given its parents. All right, so this is actually two equivalent definitions of the probabilistic assumption specified in a Bayesian network. So let me give an example now, because I think that it's much clearer from an example than in actual these definitions here. So let's talk about a chain network like this. So this network here is and I'll draw it. This is an example of a Bayesian network where we have 4 variables and this graphical structure. Right? And what this graphical model specifies for this variable here is what sort of distribution we have over these different variables. So in particular, the probability here of all the variables, so that's x1, x2, x3, and x4, this is equal to the following. So this is equal to, by actually for any distribution, the first line here holds, this will be equal to the probability of x1, probability of x2 given x1, probability of x3 given x2, x1, and probability of x4 given x1, x2, x3. Right? This importantly holds for any distribution over those variables. Right? This is just the chain rule here. We're just writing it in terms of the conditional distribution of each variable given all the variables that preceded it. That's true for any distribution. But what's nice here is that we can now use the independence properties of the Bayesian network to substantially simplify this distribution here. So if you'll note, first of all, that these two remain the same. This just equal to p of x1, p of x2, given x1. But in this one, we now have some conditional independence properties we could exploit, right? Because we know that x3 is independent of x1 given x2, right? All that matters when deciding what x3 is going to be is its parents, and it's independent of everything else given its parents. So this term here just simplifies to the p of x3 given x2. And this term here simplifies to p of x4 given x3. This is very nice. This is a very nice thing, because what we've done now is we've been able to describe this distribution. If we in fact do have these independence properties, we can describe this distribution using much fewer parameters and a much simpler distribution than we could otherwise. So in particular, this whole thing, if we represent it just as a generic distribution, it would take 15 numbers to represent, right? Because we have 16 possible values, and they have to sum to 1, so you could get 1 for free. But you have to represent the remaining 15 all explicitly. Actually, I didn't make this a poll, and it's actually on the slides. Someone's looking at the slides, unfortunately. But whoever's not looking, have their laptops open. And your neighbors don't have a laptop open either, so you can just look over. But how many parameters do we need? How many numbers do we need to take to store if we want to represent the distribution in this form? Anyone? What was that? 4? I hear a 4. Someone said 7. Can you talk about why 4?
Because there's only one parent for each.
Okay. And who said 7? Why is it 7? 2 to the first 4 times minus 1. I think is that hold for the general case here? Let's just go through it a little bit by bit here. So the first thing is that you need one parameter to represent the first one, right? Because it's a probability. So you only need to represent the probability is 1. I'm assuming these are all binary here. Did I mention that actually these are all binary? I think at least I did before. So these are all binary. And so you need one parameter to represent the first thing, right? For the next one, you need 2 parameters, right? Because for the next one, I have to specify what the probability that x1 equals 1 is given what x2 is given x1 equals 1 and given x1 equals 0, right? So I need to specify basically what is the probability that x2 equals 1 given x1 equals 0, and what's the probability that x2 equals 1 given x1 equals 1, right? These two numbers are not related necessarily. I mean, they're just 2 parameters of the distribution we both have to specify. So then if you look at all these things, there are in fact 7 parameters to specify. I wasn't quite sure if 2 to the 8 minus 1 is a general thing, because as you increase the number of parameters increases here linearly. It's 2 to the number of things minus 1. Sorry, 2 times the number of things minus 1, not 2 to the anything. So essentially, the number of parameters you need to specify an arbitrary chain would just be 2n. So this one here, you would need 2n minus 1 parameters. Whereas to represent the whole thing, you'd need 2 to the n minus 1, which is much less. Were you saying 2n minus 1? Is that what you were saying?
No, I was saying a 2 to the first because that one was like 2 to the fourth.
Okay.
Since each of them, they don't rely on more than one thing. It's like 2 to the first.
Okay, gotcha. So you got the right answer, but for the wrong reasons. So it's okay to have that sometimes, I guess. Okay. So that makes sense to everyone, sort of how we're saving some representational power here. Okay, so I have a few quick questions now about Bayesian networks, and these are actually meant to be more illustrative than things you necessarily have to know. But I want to ask a few properties about Bayesian networks. So I'm showing a Bayesian network here, so that everyone understand the structure of this network. So there's 4 nodes in this network. Nodes 1 and 2 are both parents of node 3, and node 3 is a parent of node 4. So that obviously encodes some conditional independence properties. In fact, the distribution of all these things is, I can write it down, it's actually, this term remains the same in this term, so it's just this. Instead of this term, you have, well, I'll just write it. So let me not actually cross that out because that's very confusing. Let me just write so undo that cross out if that works. The distribution of this one here, the separate thing, would be p of x1, p of x2, p of x3, given x1 and x2, and p of x4 given x3. Okay, that's the distribution that's defined by this network here. So now I have a few questions about conditional independence in this network. This is actually true, false for each of these. So the questions are x1 and x2 marginally independent? That means probability of x1 and x2 equals probability of x1 times x2. And are some variables in this conditionally independent given a third variable? That would mean in this case that is, for example, in number 2, is the probability of x4 and so x4 and x1 of x4 and x1 given x3. Is the probability of x4 given x1 and x3, is that equal to the probability of just x4 given x3? So that's what the semantics of that thing is there. Okay, so let's open the poll, and you can think about these 4 questions. All right, let's see how this looks. So this is actually pretty good. The means are in the correct answers, or at least the majority is the correct answer everywhere. So x1 and x2 are marginally independent. And I think probably the only tricky point there is just what marginal independence means. So remember, marginal independence means that, well, I wrote it there, it means that p of x1 and x2 equals the product of the probabilities. I mean, at least that's one way of writing it. And the way to get those things like that is just to say that, in this case, p of x1 and x2, and normally I wouldn't even write this because this is sort of almost trivial in the Bayesian network, but if you want to be explicit about it, you can say this is the sum over all values of x3 and x4. Again, these are going to be, I guess, these are big x1, x2. These are little ones. These are actual instantiations of the values of the product of these things. So p of x1, x2, x3, little x3, and little x4. Right? And then you plug in the expression of probability there. Because you have then conditional distributions of x3 and x4, those in the sum, you can push the sum in to there, and those just become 1. Both those two things just become the value 1. And so, in fact, it's just equal to the product. This thing ends up being just equal to the product of the probabilities. Sorry, product. I didn't say very much. It ends up being equal to that product. So essentially, you plug in that expression, those terms on the right just go away because you're summing over x3 and x4, so they both just become 1, and that's your expression there. So really, in a Bayesian network, anytime you have an expression like this where two nodes are both have no parents, they're always going to be marginally independent using the same logic there. Let's look at number 2 then. So is x4 conditionally independent of x1 given x3? That is the case. I'll actually just close this here. Let's go back to this. Number 2 is the case. That's just the definition, actually, of the Bayesian network itself. So x4, we know is conditionally independent of all its non-descendants, which are none, given its parents. That means it's conditionally independent of x1 and x2 given x3. And so it's in particular, it's conditionally independent of x1 given its parent x3. 3 is a little bit trickier. I actually think that was the one most people had the challenge with. So does anyone want to say why they think that's true? The third one. Sorry, did I say second one? Third one. Yes. Why is number 3 true? Half the people got it right. So was it just like a coin flip though? It could have been a coin flip here. So there's no evidence actually. I guess this one that people really, no strong evidence people really got that one. Yeah.
So I guess is x1 is conditionally independent of x4 is equal to x4 is conditionally independent of x1.
Yeah, that's the simplest thing. I mean, the conditional independence is it's transitive like that, right? So you can just do it that way. If you want to be a little more explicit about it, you could actually write it using Bayes' rule if you really wanted to, and the direct probabilities there. So for instance, we know that probability of, how do we do this? So the probability of x1, if you wanted to write it directly from this thing, so probability of x4, x1 I guess in this case, yeah, x1 given x4 and x3, that would be equal to the probability of x4 given x1 and x3 times the probability of x1 given x3 over, I guess, the probability of x4 given x3, right? Is that correct? Did I make a mistake? I don't think I made a mistake there. Is that correct? What?
I'm interested in x1, x4 given x3.
Right. So what I'm going to show here is that to show that x1 is conditional of x3 given x4, you can show that this whole thing equals probability of x1 given x3. That's what I'm going to show. I'm going to show the independence in that way.
Because you want to show x1 is conditionally independent of x4 given x3.
Yeah, so this is the expression you want to show. So this thing, if you want to do it this way, right? The conditional independence here means that this is equal to the product of these two things. That's conditional independence. So it's the product of x1 given x3, product of x4 given x3. That would be a to show there. So I'm showing this version of it, which are equivalent. This is just the definition of conditional probability here, remember. But you should be familiar with both of these things. So now this is pretty easy, right? Because these two terms, this term is just equal to the probability of x3, probability of x4 given x3 by the definition. So these two terms cancel. So in fact, you have that term there. So that's one way of showing it. But you can also think about it exactly the way you thought of it. It's just, this term, you can kind of think of it like this, and it's, it works the other way, so it kind of has to work this way, right? And the last one, people rightly, this is the one that actually confuses everyone the most, is that even though x1 and x2 are marginally independent, they are not conditionally independent given x3. And the simple case to think about here is something like if x3 is the XOR of x1 and x2, then even though they are marginally independent, if you know x3 and you know x1, you can determine analytically what x2 is, right? So you do not have the fact in that case that, given basically x3 could give you extra knowledge. If you know x3, you could get extra knowledge of what x1 is by also observing x2. So people were correct in this last one. I won't dwell on it because I think people got it for the most part, but this one is definitely not the case that they are conditionally independent given x3 just because they are marginally independent. Okay, so with that, let's now actually kind of forego a lot of the standard Bayesian network nomenclature, because I actually want to focus on something a little different, which is how these things are often viewed in practice. And that is as generative models. So I want to spend a little time on generative models because we're going to pretty soon, next lecture, talk about applications of these things to do Bayesian modeling, which I'll talk about a lot more next time. So the idea here is that you can also kind of think about a Bayesian network kind of as a story for how the data is being generated. So the story here, it's a very enthralling story, I'm sure, but the story is that x1 is sampled according to a Bernoulli random variable with some parameter phi1, right? Phi superscript 1. That phi superscript 1 is, of course, just the probability of x1, right? We talked about Bernoulli variables last time. So this is just the parameter of the Bernoulli distribution that's just equal to the probability that's equal to 1. So we sample, we sort of flip a coin with a weighted coin with probability phi superscript 1 being the probability is heads, and we see that lets us set the value of x1. Okay, so then given that, we now also have another parameter, which I'll call, so that was, we first flip a coin, x1, which we write as, we sample it. Actually, I should probably make those little, I use little x sometimes for the actual things, but depending on whether I mean a particular instantiation or that, I guess this could really go both ways. We say that x1 is sampled according to Bernoulli with probability phi1. Okay. Now, given phi1, now x1 rather is an actual value, right? So actually, x1 is taken on a value now. We actually has little value, say, just little x, little x1. Is equal to this, right? Now we go ahead and given that value of x1, we sample what x2 should be. So we also have a parameter that says for all possible values of x1, so that, you know, for if x1 equals 0, then our next parameter would be, say, phi0, 2. That's the probability that x2 is going to be equal to 1, given that x1 is equal to 0. And we now sample x2 according to a Bernoulli distribution with this parameter. Okay? And you sort of continue this process as such. And the thing here is that what I like about this sort of story view is this gives you a way of thinking about how samples are how samples of all the variables, right? How an entire set of samples over all the variables is generated according to the conditional distributions that we're specifying in these probabilities here. Okay. And these are all, now I'm talking about sort of concrete instantiations of all the actual variables being sampled in this way. So is that big picture? Who here has actually seen generative models before, kind of in this way? Not too many people, but some. Okay, so this is what I'm going to call a generative model, and essentially it's the same thing as the Bayesian network. I'm just talking about it in terms of sort of a story about how you generate data from these distributions, rather than a story about conditional independencies. Now, of course, these are identical; these are equivalent, but sometimes it's easier to think about these things in terms of the kind of the sequential story, where you generate, you know, a variable, you generate all the parents of a variable before that variable, then you generate the value of that variable, et cetera, and you kind of sort of continue as you go. Yeah.
I'm not sure what you said there.
Excellent. That's relevant. Okay. You had a question.
Yeah, so if we're given those probabilities phi i's,
Yeah.
okay, is it this, the Bayesian network that looks like this?
Yes. So what these, what?
Like, okay, so this is the confusion, yeah, so this is the confusion that we have. So let's say x1 you choose randomly whatever,
Okay.
and then x2 is equal to x1.
X2 is equal to x1?
Yeah, like we will choose like phi i's to be 1 or 0 or whatever.
So maybe I'll make it clarify here. So the parameters of this entire model here would be the following. There would be phi1. That would be we need one parameter to dictate the first one. The next set of parameters would be phi2, 0, and phi2, 1. Those encode the probability that this is 0, sorry, that this is 1, given this one being 0, and this is 1 given this one being 1. And then similarly, it would be phi of 1 or 0, phi 3 of 1, etc. So these are the parameters of this model here, and they're exactly the same as the probabilities I talked about before. I'm just thinking about it now in terms, and I'm writing it this way only because this is how I defined a Bernoulli distribution. It's governed in terms of these parameters. So I'm talking about it now in terms of a distribution, you know, in terms of a sampling procedure for these random variables.
Yeah, so let's take phi1 to be 1/2, and then phi2, 0 is 0, phi1, 2 is 1, and then phi3, 0 is 0, and phi3, 1 is 1.
Okay.
So this literally means that x2 should be equal to x1 and x3 should be equal to x2.
Okay.
But then it's not true that x3 is independent of x1.
So it's independent of x1 given x2. So if you know x2, it's then independent of x1. I mean, it's a little odd to talk about in terms of when they're deterministic, but again, it's independent of of all the things that came before it, given its parents. Yeah, so it still has the same probabilistic semantics. And actually, it's fine for them to be deterministic. That's okay. That still works. It's a little bit odder because they're not probabilities anymore. And actually, some other algorithms don't work well in that case. But here we're fine. Okay, so what I actually want to talk about here, and this is what we're going to talk about more next time, but I just want to give a little bit of preview of it, is sort of some of the power of modeling things in this way. Because while this is sort of simple, it's very trivial to write down things like this, there are much more complex models you can write down very compactly using this notation of generative models that are a little bit harder, or at least a little less intuitive to write down, or rather maybe even think about as Bayesian networks. So I want to just highlight two of these, two simple ones for right now. One is called naive Bayes, and one is called a Gaussian mixture model. So we haven't talked about these. These are sort of common machine learning models. We haven't talked about them here, but they are very common machine learning models, and they're actually very simple to describe using this notation of generative models. So naive Bayes is a distribution over pairs of variables x and y. So naive Bayes says, actually, I'll just start using this one here. So naive Bayes, the naive Bayes models, is actually a distribution over pairs of variables x and y, where x is usually thought of as being, x is going to be, okay, yeah, so x is, say, it's categorical, but it's actually, it's categorical, well, I'll just say it's xi is categorical. That means it can take on one of categorical. It can take on one of k different values. They actually could be different k's for the different variables. Doesn't really matter here. And y is binary. It actually could also be categorical if you want it to be. But essentially what naive Bayes says is the story of the distribution is that I first sample y. I first sample what ends up being my class label, just like in a regression model or a classification model, except sort of this is implying a generative model over how you come up with your data. So I come up with my data by first sampling y from a binary distribution, and then given y, I'm going to sample each of my xi's independently based upon that y. So essentially, I have a parameter that dictates my distribution over y here. So y is going to be Bernoulli with some parameter phi, and then xi given y, and I'll say even given y equals some value little y, this is going to be categorical with the phi variables of phi I, y. So the parameters of this distribution would be phi I for 0 and 1, for I equals 1 to say n, where n is the number of x variables that we have. So we're not going to talk about how then you do sort of prediction based upon this, but you can also then, if you want to predict what's the probability of y given x, some observed x, you actually can compute that using Bayes' rule. And that's just sort of the naive Bayes algorithm put very simply, but the core principle there is you think of it as a generative model. Again, these are just examples that you're sort of not really meant to fully understand the algorithms here, but they're just sort of examples of models that we typically describe using this generative process. So another very common one is called a Gaussian mixture model. In this case, y is a categorical variable, so I'm going to sample y. I'm calling it z here. I'm going to sample some variable z from a categorical distribution with some parameter phi. Again, this is categorical with k components, so phi here would be a number 0, 1 to the k that has to sum to 1. And then once I know my z, I sample x given z is equals, say, some little z as being normal with mean mu z and covariance sigma z. So that what that means is, for each setting of z, I have some mean and I have some variance. And the way I generate data from this process is I first flip a multi-sided dice to find out which, a weighted multi-sided die, I guess, to find out which z is my underlying variable there. And then given that z, I sample from a normal distribution to find my final variables of x. So for example, you could represent a distribution that looked like this using this. So if you have this distribution here, if I wanted to come up with a distribution that had the kind of this density, I could basically have two variables. I could have a binary z variable, and I could have essentially mu1 be here and mu2 be there, and then phi is, say, 1/2. It's Bernoulli in that case. I actually specify the first one, but that's the basic idea. And they could have some covariance each of these. So using models like this, you can describe kind of very rich probabilistic models that don't necessarily have a nice closed form expression to them, but which still capture sort of very nice independence properties amongst your variables. I'm just going to say a few more. These I'm not going to go into detail to describe, so I just want to highlight the fact that these things exist too. The first one is actually linear regression, or in fact, what's called Bayesian linear regression can be also thought of as a graphical model. Though in this case, I'm just talking about normal linear regression, actually, I realize. So remember, our maximum likelihood model that we use for linear regression, rather, the reason why we came up with this squared error was that the squared error is sort of the maximum likelihood estimate for a Gaussian random variable. And so I can actually write that kind of mathematically now as saying that I have some parameters theta and I guess a covariance sigma squared here. And the random variable y, given my inputs, is going to be normally distributed around the mean theta transpose x with some covariance sigma squared. So this is actually a probabilistic distribution, a probabilistic model of that kind of maximum likelihood estimate of least squares that we talked about last time. Or at least it's in the notes. I forget if we got to that last time, but that one was in the notes too. So it's just a very simple kind of probabilistic model of what least squares regression is actually doing. These I don't really want to get into these too much because we're going to talk about them a little bit more next time. So I'll kind of defer this for next time. But there are much more complex models you can have here is the point. So a common one here is a change point model. This means that x is sampled uniformly between 0 and 1. So basically I have so the kind of data that this thing generates, it looks like this. So I sample a x between 0 and 1. So I sample x, say here. And then I use one mean for x if it's less than that point, and I use another mean for x if it's greater than that point. So now I sample, say, several y's, and maybe I have a mean up here, mu1, so this is y, this is x, and I have mean u2 here. So my data will look something like this, lots of points here, and then a change in my data here, and lots of points that come from down there once I'm beyond my change point here, x. Actually, what did there shouldn't be a t there. I don't know where, something got deleted there because there shouldn't be a t. It's basically given t is sampled in the form of that, and then x, y is sampled, y given x and t is sampled according to that. Anyway, actually I'll fix that for next time because we're going to talk about that next time, so I'm not sure actually where t was supposed to mean there. The next one, though, is actually a very common model, which is now getting fairly complex, called latent Dirichlet allocation. This is what's known as a topic model. So essentially what we're trying to do is we're trying to take a collection of documents and ascribe some number of topics to each document. And the model here is that the way you generate documents is that I first pick my topic essentially as a multivariate. I sample my set of topics from what's called the Dirichlet distribution, which gives me some distribution over topics. Then I sample essentially a bunch of words, which are a distribution of words for that topic, and then I pick essentially at random, from a bag of words for each document. I say I select what the topic of the ith word should be, and then given that topic, I select what the actual word is. So for each document, the way I generate it is I sort of take the words, I pick a random topic for each word, where the topic distribution is sampled according to this thing. Then I pick given the topic for that word, the distribution of topics for that word, I pick what the actual word is, given a different distribution here. So this is actually getting quite complex, but it turns out that this topic model is actually one of the more common ways of trying to look at a sort of completely unlabeled corpus of documents and figure out a consistent set of topics that actually cover those documents. I showed an example of it at the very beginning of the last lecture, and actually this is the entirety of, in some sense, the model that actually generates this distribution here. Yeah?
There we were trying to classify the words in those documents into some.
So no, so the topic modeling really is not about classification so much. It's about sort of just describing what topics there are in a document. The difference is that there's no true labels actually given to the document. So I don't actually say this document is, point 5 about the law and point 2 about, finance, etc. What I'm really doing here is I'm just creating a model of how documents are being generated, and then according to this model, I'm kind of learning what the parameters of this model is, which essentially correspond in the end to some, if you do it right, correspond to some kind of coherent topics. Like these words all seem to belong to one kind of group, and that ends up looking a lot like those words are all legal words. This other set of, this other topic corresponds to a different set of words that all look like finance words, and so that's sort of the finance topic. But all of that is discovered by the algorithm. So none of it's actually given in this kind of labeling of the documents. It's just all sort of ascribed after the fact. It's all kind of discovered just based upon the structure of the words, and then we can kind of give it a label of like legal words after the fact.
So you you train this structure based on some data where you classify the words into different topics, or how do you actually come up with the type?
Yeah, so again, I'm not really talking about this particular model here too much. What it is that essentially we are going to try to actually, let's see. So alpha and beta here are sort of meta distributions over the distribution you actually are really going to sample from. So for every, for when I start, I basically sample a set of topics from a recent distribution. And what inference is going to involve is essentially trying to find out what these parameters are given some actual documents. So given some documents, in other words, if I'm given basically just this, a bunch of documents and words, how can I infer what the value of the other parameters are? This is what's called an inference problem, which is what we're going to get to actually next. Here I'm really just highlighting the fact that these things can get pretty complex quickly, but you can create kind of very rich generative distributions that kind of describe how your data is being created. Oh, yeah.
Just to make sure I'm not missing something, in the last line, should that J be ZIJ, should that J be like reduced?
Oh yeah, I guess it should be with the Z here. It's ZIJ is the topic of the ith word in the jth document. And the and then this one is categorical with distribution. Again, I don't want to dwell too much on this particular example here because this is sort of almost incidental, but I do want to emphasize that these things are sort of really used in pretty complex models here. All right, so we'll see how far we get actually. I might have to cut out a lot of the actual proof here if we can't quite get to it. So, all right, so let's talk about probabilistic inference next. So the inference problem says essentially more or less, and I guess I'll clarify there are a few different types of it in a second. But what the inference problem says is, given some observations in a model, how can I find a distribution or maybe generate samples from or find the most likely assignment of the remaining variables in my graphical model? Right? So the point I want to make actually is that there are multiple different kinds of inference, but the one we're going to focus on the most here is the case of some variables in our model being what are called observed variables. In other words, for whatever reason, we actually see what the value of these things are, and we want to infer the value of other variables that we don't see. And the way we're going to write that is with grayed out circles and normal white circles. So what this notation means, this notation up here means that x1 is observed. In other words, we actually know what the value of x1 is. Someone tells us x1, you thought it was a random variable, but I'm telling you in this case, x1 actually takes on the value 0, or maybe it takes on the value 1. So what that notation there says is that x1 is actually observed. And so now the question is, how can I, in this case, come up with a representation over the remaining variables in this setting? Okay, so x1's observed now. I'm going back to my, of course I erased this one before, but I'm going back to my sort of chain setting. Do I have it here? No, I don't. Where my distribution is specified according to the following. P x1 to x3 x4 equals P x1 P x2 given x1 P x3 given x2 P x4 given x3. Okay? And someone tells me what the value of x1 is. Okay? So how do I go about coming up with a description, essentially, for what the distribution over the remaining variables is? Actually, does anyone want to hazard a guess on that?
We just try to sample from it, right? Can we find it analytically?
We don't need to, I mean, here we actually don't need a sample from. Sampling is going to be one of the main ways we actually do consider inference, but here we don't need a sample from it.
Delete x1 and what is left is actually another Bayesian network that could be left with.
Yeah. So does everyone understand that? So essentially what you're doing here is if x1 is known, then essentially this first term disappears. So say x1 equals 0. We're told that. Then now we have a distribution over just the remaining ones, where its distribution is just essentially, we get rid of this, this term falls, this term disappears, and we replace this one with probability x2 given x1 equals 0. The rest stays the same. The rest we just keep as it was before. That is now a Bayesian network over the 3 remaining variables. There's still a compact form for those variables that represents the distribution over those 3 variables. All right, so does that make sense? Any questions there? So now a little bit harder problem though. What if we observe x4? How do I come up with a distribution over the remaining 3 variables if I know x4? Any guesses? Yeah. So Bayes' rule. Okay, great. That's exactly right. So how would I do that? So basically, I just would say, actually, yeah. What's on the left and right hand side in Bayes' rule?
So the average distribution P of x3 x4 is equal to P of x3 given x4 upon P of x4 into P of x4, and on the other side you have P of x4 given x3 into P of x.
Okay. Maybe I'll write it like this. I'll just write it in the general case like this: P of x1, x2, to x3 given x4, basically equals whatever value it takes on, right? This is just going to be equal to P of little x4 given given x1, 1, 2, 3 times P of x1, 2, 3 over P of x4. Right? This is going to be a constant down here, though. So you can write like this, and you can actually then sort of plug in the form you had of this expression to come up with variables for all these things. And some of them will simplify, some of them won't. Right? Some of them will kind of simplify. Maybe you can come up with a nice thing, but probably you're actually going to end up doing quite a bit of math there to get kind of a nice compact form of the distribution. So you can do that. That actually is not, it's very doable here. It's completely doable, and it's exactly how you would do it. You would just apply Bayes' rule. But this is getting a little bit complicated, right? So imagine now this network we've had in our poll 2. How do you come up with a distribution over that, say if I'm given x3? Things start to get a little bit nastier here, as you might kind of imagine. And so what we're going to do is talk a little bit more broadly about how we solve these inference problems. And I'll in fact define several different types of inference problems that we're going to be concerned with here. Though the main one we're going to talk about in this case is the last one, which is a conditional inference. So the first type of inference is called marginal inference. If you're given some distribution over a bunch of variables and you want to find the probability of some subset, you're essentially summing out over all possible variables of the remaining ones to get a distribution over just the ones in x sub I. Map inference is a little bit different. We won't talk about that at all here, but it is kind of an important idea that does come up a lot. This is the problem of just finding the most likely assignment to variables. So rather than finding kind of the probability of any assignment, you just find the most likely assignment. Say I'm doing my classification with a naive Bayes model. I maybe don't really care about what's the exact probability of different values of y. I just care about what's the most likely y, so I'm just going to predict that one. So maybe I can do something a little bit simpler in that case. The last time, which is the one that we're actually going to focus on, is really both these things have conditional variance. So there's lots of cases where you know some setting of some of the variables, and I want to determine what's the value, what's the probability distribution over the remaining variables, or even over some subset of the remaining variables here, where I guess I and E here would be, of course, disjoint sets. So all these things are kind of called inference. And there really are three main approaches. Yeah?
Sorry, what does MAP stand for?
MAP stands for maximum a posteriori. It's the maximum posterior probability value. But it's actually come to mean more than just posterior. It can mean actually even, it doesn't have to be conditioned on anything. It can be unconditional too. So that's what, but it's just the common name for what it goes by. I didn't write it because this doesn't always make sense to use that term, frankly, but that's what it's come to mean. People actually try to avoid that and say call it MPE, which stands for most probable explanation, but that's actually a less common term. So I call it map inference. That's what it typically is called. All right, so before I dive in too much into any single thing, I just wanted to emphasize that there are actually three main approaches to approaching these inference problems. The first one is going to be exact approaches. So the first approach is, can I actually formulate exactly what my distribution that I'm after really is? If it's small enough, can I just enumerate every single possibility? That might be doable if it's, if I just want to find, say, even if I have a very big model originally, maybe I just want to find the probability of a couple variables, which I could enumerate exactly. So maybe I can just try to find the probability of just those variables. Or maybe I can represent the remaining variables as an actual Bayesian network, as I did here, right? So that's another compact representation of the remaining variables, given some setting of the original variables, or of the observed variables. The one we're going to focus on mainly is a different approach, though, which are actually sampling-based approaches. So the problem with the first one, which we'll get to in a second, is that oftentimes this is just not tractable. Even for graphical models that can be written compactly, that have a very nice compact expression, you oftentimes can't actually solve inference problems using the same kind of compactness of representation as you have in the original graphical model. And we won't really cover that too much, but just know that the first one, unfortunately, while it sounds great, is actually oftentimes not really doable in practice. And so for the most part, actually, if you look at a lot of AI techniques or a lot of AI applications, people do really tend to use approximate methods. And the approximate methods break down into two main categories. The first category are these sampling-based approaches. This is just saying, maybe I don't care about representing my distribution exactly. Maybe all I care about is the ability to draw samples from that distribution, right? Which is, if I can draw samples, enough of them, I can pretty much answer any question I have anyway. So maybe just getting samples is a good enough approximation there. And the second one is a different technique, which we're not going to talk about too much, but you should sort of be aware that it exists. That's called, which I might try to highlight a little bit if there's time next class, but maybe not, which are called variational approaches. And these approximate distributions over the hidden variables, these are the ones we don't observe, using simple distributions. So if you can't represent the entire distribution of all the hidden variables, you approximate it with some simple distribution, and then you try to make that simple distribution as close as possible to the true underlying posterior, measured with some sort of divergence term. And these are actually oftentimes the more powerful technique, but they actually do need to oftentimes also be specialized more to the particular form of the model, and so they're a little less kind of black box in general than the sampling-based methods. So the big picture, though, is that these are the three categories of approaches. We're going to focus mainly on the second one, but they all do have their use. So let me, in the time I have, I'm sure I won't be able to, unfortunately, get to the big thing I was hoping to today, which is the sampling-based methods. But let me just mention quickly some of the techniques involved in exact inference. So the first thing is that exact inference in the simplest case actually can be solved with an application of Bayes' rule. So we talked a little bit about this mixture of Gaussian models. So we had actually even right there. So we first sample a categorical variable from some categorical distribution, and then we sample after that we sample a Gaussian, depending on what the value of the categorical variable is. So one of the things you want to actually do in mixture of Gaussian modeling is you want to be able to compute, well, what's the probability over my different discrete variables given some observed quantity x. So given some observed quantity, what's the distribution? How likely is it to become from each one of these different sort of modes of my distribution? And the way you do that actually is very simple. It's just with Bayes' rule. So this just becomes the probability of x given z. That's just going to be the likelihood of a Gaussian distribution times the probability of z. That's just going to be my categorical variable phi, divided by just the sum over all these things. The sum over all little z, p, x, z, p, z. Right? And that will give you the distribution over all possible values that categorical variable can take on. There are certainly cases where you actually can also extend this to richer settings. So let's take a simple example now, get back to our chain that we like so much here, and talk about how we could represent the probability of x4. So if I want to know from this thing what my distribution over x4 is, despite the fact that looks kind of hard because unlike x1, say, I don't have the exact functional form of x4 specified anywhere by my model. This is an example of a marginal inference problem. We actually can still do a perfectly good job with this because we can kind of exploit the properties of this graphical model structure to actually come up with a pretty easy solution there. All right, so the way we do this is we essentially want to say p x4 is going to be the sum of over x1, x2, x3 of my joint probability, but I'm going to write that already kind of in its factored form, p x1, x2 given x1, p x3 given x2, and p x4 given x3. Now, naively, what you would do here is you would just take every single possible assignment of all these variables, and you would just sum over all possible assignments, all two to the 3 assignments. But that actually ignores all the actual structure in your model. So what you can do here is actually rearrange some of these sums. So essentially, if we want to sum over x3, we can notice the fact that these two expressions here do not depend on x3. So we actually can write this as the sum over x1, x2. Actually, let me do it the other way. Actually, let me do it this way instead. Let's sum over x1 first. That one's easier. So instead, we can basically use the fact that these two terms do not contain x1 to write this as sum over x2, x3, p x3 given x2, p x4 given x3 sum over x1 p x2 given x1 p x1. Okay, so I've basically taken some of the terms of my sums outside the summation. And now I can actually compute this very easily, right? I can just sum out x1 in this case here to essentially come up with this term, which is just also, by the way, equal to p of x2. I store what that probability of p of x2 is, and I repeat this process, and I get eventually a distribution of just p of over x4. So the big picture point here, and I don't want to dwell on this too much because, again, as I said, these things, this is sort of actually an illustration of a general procedure called variable elimination, which is quite broad. It actually is quite general. And it works great for things like these chain networks where you know exactly how to eliminate the variables. You sort of start at the beginning or start at the end, depending on what you care about, and you sum out the variables accordingly. Variable elimination can work great in those situations. And so for some models like hidden Markov models and things like this, if you've heard about those, you can do exact variable elimination and run exact inference using these methods. However, they don't really work for general models. Even when you have something simple like a continuous random variable, even if you can't exactly compute an integral or something like that, you're sort of stuck here and you can't really run these methods. So they just aren't that practical for the majority of what we actually want to do with probabilistic modeling, and so I don't want to spend too much time kind of harping on them. So just let me illustrate that actually by just show us a really simple example where we really actually can't do anything but the really sort of most naive thing of enumerating all possible variables here. So this is a really simple example where essentially I have a bunch of Bernoulli random variables, and then I have some, so the zi's here are all binary random variables. They're 0 or 1. And then I have a final observed variable x, which is some sum of all these things plus some random noise. So essentially here x, another way of writing this is to say that x is equals to essentially some weighted sum of these things. So from I equals 1 to n of theta I zi plus some noise term where the noise term is normal, means 0, and sigma squared. Right? So this is a pretty simple model. It's also sometimes called a subset sum problem, for those that have heard about these things before. But basically, I'm just taking a bunch of random variables. Bernoulli random variables, computing some weighted sum, and I observe that sum. The question then is, what is the posterior distribution over all my random variables there, given an observed value of x? Right, so how do I actually determine what those variables are given x? Unfortunately, this actually ends up being a very hard problem. I really can't do much other than just enumerate all possible settings of all my z variables and determine then what's the probability of observing that variable x under those things, and then apply Bayes' rule in kind of the most naive way possible by just coming up with an expression of what the probability is for every single possible assignment, all 2 to the n assignments of my variables z. So again, don't want to harp on this too much because this is really just all I'm sort of illustrating here is that there are really natural examples where you would like to be able to run an inference procedure to determine what the probability of just say, I mean, even just for this question, what's the probability of that z1 equals 0, right? That's not that complicated. It should just be a number. But what's the probability of z1 equals 0 given some value of x is just not something I can answer with exact inference. I can't answer it actually exactly. And so because of this, though this problem actually ends up being hard for the other methods too, but because of these kind of issues, we often do kind of resort to sampling-based inference methods instead of trying to solve the things exactly. So let me just give the broad intuition now, and we'll delve into the details. I'll just present the details, and depending on how much time I think I have next time, I'll either give the proof or not. I'll just leave it in the notes. But I want to talk a little bit now about sampling-based methods and kind of how these things work and kind of what they are doing, because they really are by far the most common technique currently in large-scale probabilistic models in AI. So the basic idea here, before I start, though, any questions? Because we're almost out of time, but I want to give the high-level overview first. Okay, so sampling-based inference. The idea here is that if we have a setting like this, and maybe I can't succinctly describe, I mean I could here as it was pointed out, but if I can't succinctly describe the distribution over x1, x2, x3, or maybe even better here, maybe I can't succinctly describe the distribution over all the z variables here, other than just enumerate them all. Maybe I can do something a little easier, which is to say I can just try to draw samples from the distribution over these hidden variables, given my observed variable. And from that, I can sort of do whatever I was going to do anyway with my probabilistic model, right? If I want to know what's the probability of x1, I can just generate a bunch of samples, take the average of those samples, I can do that. If I want to know what's the probability of x2 given x1, I can do that too with sort of these sampling-based techniques. And so being able to generate samples in some sense is kind of almost as good as being able to describe the distribution compactly, if all I want to really do is look at those samples or compute some simple statistics of those samples. And so this leads us really to a domain called, well, actually before I mention that, I'll first mention sort of one really naive way of doing this, which is something called rejection sampling. So what I could do, I mean, we know how to generate samples from kind of this whole thing where all the variables here are white variables, right? We talked about that as our generative model for this chain here. So the way I do that is I generate, first x1, then x2 given x1, then x3 given x2, then x4 given x3, etc. And so one way to sort of do what I want to do is just essentially do that sampling process and then throw away all samples where x4 doesn't actually match my observed x4 there. So that would be a way of generating, and I just keep those samples that do match my observations, and those are in fact samples from the distribution that I want to sample from. So everything seems good. So what's the problem with this actually? Yeah.
If the probability of the observed variable is really small, you're like going to get no samples.
Exactly. So if the probability, so say I observe x4 equals 0, and however this model will set up, the actual probability of x4 equals 0, computed this way, say, is 10 to the negative 8, right? It will take me 10 to the 8 tries of sampling before I get one sample where in fact I observe this. And so it takes me 10 to the 8 cycles of sampling before I get one sample. And if I want to, of course, usually get more than one sample, I need to do something better than that. And so I have to actually repeat this a whole lot of times before I can get a reasonable size sample of my distribution. So this isn't, while this sort of is a very nice way of doing it kind of conceptually, and if your observation has high probability, actually it's not a bad way of doing it, right? If you're in the other case where this is like 0.5, then maybe this is a perfectly good thing to do. You can just sample and throw away the things that don't match, and you're all set. But the reality is that for most of the distributions that we specify, like for example LDA, which I said here, again, not knowing anything about this model here, the way that this model generates words is it again reaches into a bag and picks each word according to a topic and just throws them all in a document, right? And so the number of times you have to sample documents until you come up with one that looks exactly like the one that you've seen, it's like the monkeys typing on typewriters, right? Until they type out the script of a Shakespeare novel. You're never going to actually see what you want to see. And so you need other techniques that will actually tell you, given some observed data, how can you actually generate a sample over those things that are not observed. And this leads us to a domain of algorithms called Markov chain Monte Carlo algorithms that I'll describe either briefly or in some detail next time, depending on how much other material we want to cram in. But that's sort of the broad introduction to these sampling-based techniques, and we'll talk a lot more about it next time.